Okay, off we go. So last time we were talking about change of variables, and we finished our discussion of two-dimensional change of variables. So we're going to move on now and talk about three-dimensional change of variables. And guess what? Good news, as you probably would expect, it's morally equivalent. It's the same basic idea. Suppose you are looking at some integral, right, for which the domain is, I'm going to say, undesirable, such as I think we'd agree this is an undesirable domain that I've kind of, approximately drawn here. I mean, think about all the bad things that would happen if you start slicing this up, right? You're going to hit corners just all over the place. The cross sections will not be rectangles. Within those cross sections, slicing them up, you're going to be hitting corners all over the place. This is a nightmare of a domain. Gosh, it might require chopping it up to 20 pieces, right? Just insane. Okay, so the big idea is if you can view that as being an image, right? If you can view that as being an image of a different domain, such as, for example, this right here, then you can do, as we did in 2 dimensions, a pullback, where you're basically just plugging in what the change of variables function g tells you to do, right? X, y, and z are explicitly functions of u, v, and w, as given in the change of variables function itself. Just plug those in, right? And the one little detail you have to worry about, what to do with size, right? And size is understood as being a stretched out version of size in your pullback domain. Again, there is this stretching factor. That stretching factor that you just have to remember to insert, basically, right, that accounts for how much volume in UVW space is stretched out to become volume in XYZ space. Same formula. It's the absolute value of the Jacobian determinant. It's really convenient. It's exactly the same idea, just 3 variables instead of 2. Now, of course, just a couple of observations. That means your derivative matrix is now 3 by 3 instead of 2 by 2. So it is bigger. Computing its determinant is a little bit more trouble, right? I mean, but it's, again, strategically, big picture, the same. Okay, I am going to show you an example of this. Before we get into the example, I want to write down a cool fact. We've actually already seen an example of this cool fact. That's this theorem right here. And that is that if you have a linear transformation, keep in mind linear transformations can always be represented by a matrix. Beautiful fact, the matrix representing the linear transformation is also the derivative matrix of the linear transformation. So we saw this in the example about rotations. You might want to flip back and look again, take a closer look if you didn't notice or if I didn't explicitly comment, I don't recall. But we've, like I say, already seen an example of this working out. This is easily confirmed. All you got to do is write down any matrix A. Right? Keep it general, ABC, that kind of thing. Okay? Write down the corresponding linear transformation. Find its derivative matrix. You will find it is exactly the same as the original matrix you wrote down. So, neat fact. Make sure to check through that and confirm for yourself and satisfy yourself that this is, in fact, always true. As always, come with questions to office hours if you'd like to see more. We're going to use that fact in this example here. This is a powerful example of how awesome change of variables is in 3 dimensions. We're going to entertain an integral on a domain here, which is a parallelepiped, and this may not look like a bad domain, but it is. This is an absolutely horrifying domain for an integral. Let's just talk through real quick why this is horrifying. Easy to, at a glance, notice that a parallelepiped has 8 corners. Generically, one of those corners is going to be your first slice, one of them is going to be your last slice, and the other 6 will be in between. So you're going to hit 6 corners as you slice this up. That's just on your outside slicing. Now, keep in mind, on each of those 7 pieces that you slice it up into, those cross sections are not rectangles, right? They're Best case scenario, they're triangles. But many of them are quadrilaterals, even hexagons. So each one of them, as you slice it up, is going to be hitting a bunch of corners. This is a nightmare scenario. Right? Is everybody on board with that? You see why this is terrible? Right? We really don't want to have to brute force this thing. Okay, so here's the big idea. We have to import an idea from linear algebra. Neat fact, easy to recall, easy to argue. If you are given the edge vectors of a parallelepiped corner at the origin, like this, you can view that as being an image of the unit cube in a very convenient way, right? If you know these edge vectors, you want to view your parallelepiped as being an image of the unit cube, all you got to do is take those edge vectors, make those the columns of your matrix, like I did here. That's it. Wonderfully simple, wonderfully convenient. Now, let's just very quickly, talk through why this would be. I mean, how could we be so lucky? And just think about the edges, the corresponding edges of this unit cube over here. They're the standard basis vectors. What are the images of the standard basis vectors when you put them into this linear transformation you've defined? Well, we have a rule for that. The images of the standard basis vectors are the columns, which we have cleverly made to be these edge vectors, right? So by this very convenient construction, the edges of the unit cube go to the edges of the parallelepiped, and linearity takes care of everything else. And that's another exercise in linear algebra. And again, if you're curious, you want to see more details on that, come to office hours. I'll be very happy to walk you through it. Very convenient little trick we're going to pull here. And we've got ourselves a matrix, which means we've got ourselves a linear transformation that gives x, y, and z as functions of u and v. Everybody on board? So we wave the magic wand called change of variables, and we pull back, right? The pull back through that linear transformation. Change of variables function gives us an integral du, dv, dw. And on the unit cube, you gotta love it, right? Everybody's favorite domain for a triple integral, right there. The bounds are 0 to 1, 0 to 1, and 0 to 1, right? And all constants, all convenient numbers, just thing of beauty. And now it's all over but the details. There are a couple little details to talk about. One is, what is the stretching factor? And of course we need to know the derivative matrix. Well, recall, the derivative matrix is the matrix for the linear transformation. That was our theorem that we mentioned just before this example started. So there's your derivative matrix. Nothing to it. You got to compute its determinant to get the stretching factor here. A little bit of arithmetic. Could be worse. And then there's the question of what is our integrand. Keep in mind our original integral that we were looking at here. Here it is. This is our original integral. And here it is written again. What is this z? All right, what is that? Well, easy to forget, but also easy to execute. That you've got to realize z is the third output of your function there. And your function, don't forget, is given right here. And the outputs are part of x, namely, what we're looking for here, z being the third coordinate of the output, we're looking for the third coordinate of this matrix product, a times u. And you get that from looking at the coefficients in the third column, third row of your matrix for your linear transformation. So these being the coefficients means that our z is just that right there. Is everybody good? So Really nice simplification, right? Again, nightmare scenario of I don't even know how many pieces we'd have to slice this up into. Horrifying, right? And one pullback by a clever but easy to write down change of variables, linear transformation, and we pull back again to the world's easiest domain, and boom, nothing to it. Okay, so I think this is a great example. Okay, and with that, we are going to move on now to another really fantastic example of change of variables. Not always thought of in that way. Different books present this next idea in different ways. I think there's tremendous value in viewing this as an example of change of variables. That's why I'm going to present it this way. Anyway, here we go. Let's talk about polar coordinates. Y'all remember polar coordinates from way back. Recall that I pushed this point of view that I want to think of it as a function. It's a function where r and theta are the inputs, and then x and y are the outputs. And check it out. That means that this has all of the features necessary to be a change of variables function. Right? We didn't think about it in that way at that time, obviously, right? We didn't know what that was. But understanding polar coordinates as a function means you can explicitly use it as a change of variables function. And with that in mind, well then, hey, cool, all I got to do is compute the stretching factor, and the stretching factor is various partials that you then take a determinant, et cetera, et cetera. Our Jacobian determinant is r, as it turns out. By the way, healthy exercise. Everybody should fill in the little yada, yada, yada right here. No big deal, easy computation. Make sure you can do that, though. It's a really good little exercise. And great. So once you know your Jacobian determinant, then your stretching factor is just the absolute value of that thing. And so now this is arguably a stopping point for this computation. Most people, though, don't stop here, because our stretching factor, being an absolute value is very important. It's a big deal, right? But it's kind of inconvenient. Nobody likes absolute values, especially if they're inside of your integral. This is no good. Nobody wants that. So here's what I encourage, and vast majority of people do this, and that is to make a choice, a certain particular choice. We choose to require r to be positive. You don't have to. Right? There's no law that says that you have to do this. There's no mathematical reason that you should have to do this. But it really is a good choice, and I strongly encourage it. Because if you make this choice, if you choose to only look at polar coordinates that have r being positive, then check out what happens. If r is positive, then this thing we're taking the absolute value of is already positive, and that stretching factor in that case then turns out to be the already positive, therefore no absolute values necessary, r. And that's a good thing, right? That's very convenient for our integrals. Is everybody on board with that, and why this is a choice, and why I encourage it, but why it is not mathematically commanded, right? It's just clever. All right, so we're going to see a bazillion examples in today's lecture, in this section, and then to follow in many subsequent lectures. Many examples are going to come up where we use this as a change of variables function, and this, therefore, is our stretching factor. So you really should memorize this formula. Very conveniently, it's an easy one to memorize, right? But do make sure to memorize it. Cylindrical coordinates. Same thing. This is a situation where thinking of cylindrical as being three-dimensional polar coordinates is actually really convenient. Most of what's happening here is happening kind of in a polar sense. Z isn't really doing anything in this scenario. If you don't believe me, you can write down the 3x3 derivative matrix. You can compute that Jacobian determinant. Now again, everybody should do this. This is a healthy exercise. This one's a little bit more trouble because it is a 3x3 determinant, but works out very nicely. Again, just R. And for the exact same reasons then, with our stretching factor being the absolute value of R, we're going to make this same choice. Again, you don't have to. Again, it's not mathematically required, but again, it's a really good idea. Choose R to always be positive, in which case your stretching factor is the absolute value of something that's already positive, and you can lose the absolute values, which of course, big win. So really ought to do that. Okay, well that was easy. It's just a repeat of something we've already done, basically. Now spherical coordinates. And here's where things do get somewhat different. But it remains that spherical coordinates you can think of as a change of variables function. 3 in, 3 out. You can totally pull back through that. Likewise, you can totally compute the Jacobian determinant. No problem. It's inconvenient. There's a bunch of trig in this calculation, right? Now, again, I think it's a healthy exercise. I encourage you to do this. It uses the Pythagorean trig identities several times, right, in simplifying it out. Like I say, everyone should do this once in their lives, so I encourage you to take a crack at it. And what you will find as your answer is this formula right here, rho squared sine phi. That's your Jacobian determinant. That is the thing whose absolute value is your stretching factor. And again, now, we find ourselves in this circumstance where we've got these absolute values in our integrand. Nobody likes that. How are we going to get around this? So here's where a lot of students make a mistake. A lot of students mistakenly think that, well, look, rho is kind of like R. And so if up here the answer was to require rho to be non-negative, maybe down here I should just let, I think I said that wrong. Up here we required R to be non-negative. So down here maybe we should just require rho to be non-negative. Does that fix it up? Not even close. Well, why would it? The rho is going to be squared. Let rho be negative all you want. Who cares? It does not affect our situation. If I want these absolute values to go away, if I want to know for sure that this blue Jacobian determinant is non-negative, what I need is to worry about this sine phi. How do we make sine phi guaranteed non-negative? Well, we restrict ourselves on phi. Right? Specifically, I need phi to be between 0 and pi. So we make this choice, and with that choice, then absolute values go away, and life is good. Yes?
Are you only allowed to make that choice when you know that it'll still be able to cover all the points within that restriction?
Well, that's always true. I mean, you can always get it. There are always spherical coordinates for any point that has phi between these values.
Like if it's not a nice spherical symmetrical.
Yeah, I mean that's right. There are situations where it could be. I could make up a scenario where it could be very convenient to use values of phi outside of this range, and then you'd have to make a tough choice of, do I want to follow this rule and deal with the inconvenience of whatever geometry that is, or do I want to break this rule and now I've got to deal with absolute values? Okay. And frankly, I am having a hard time off the top of my head. God, never say never, but I do not have any example prepared, nor have I ever seen an example where that would be a good idea. Yeah. So I'm going to say, again, never say never, right? But I don't think it's worth worrying about. Yeah. So there you go. Phi. Strongly recommended that you always make choices that put phi between 0 and pi. Okay, one last word about this, and that is if you look at our urged choices, phi between 0 and pi, r positive, and then likewise up here, r positive, non-negative, of course. You look at these. Why is that not? Here we go. You look at these choices here. these are values that I like anyway, right? I mean, I personally, and I think probably all y'all, I prefer positive values of R, right? It's just more natural usually to think things that way, and I prefer values of phi between 0 and pi. It gets really weird when you pick different values of phi, right? That's where things get confusing. So the beautiful thing about this is if you impose the requirement on yourself of choosing the values that you want to choose anyway, right? Then you get the added benefit of getting to lose absolute value. So it's a total win-win. So there's really, very hard to come up with an argument against wanting to make these choices. Okay. All right. Okay, moving along. Let's see an example of this in action. So we consider the first quadrant portion of the unit disk, like so. That is the domain for our integral down here, and now we look at this integral, and let's come at it sort of head on. Let's do this in rectangular, the usual, just slice it up as it is. And there's a curve up here that is going to mess up our bounds. You'll notice that in particular we get a square root in our inner bounds, which means we're going to have a square root in the integrand of our outside integral, and that is not good news. Now, it's not that it can't be dealt with, right? There are trig substitutions, which, by the way, this is a reminder if I haven't said it before, trig substitutions come up a lot in the real world. So engineers, physicists, etc., the world's full of circles. Circles make square roots. Square roots necessitate trig substitutions. So it's very, very regular. I do encourage you to try to get good at trig substitutions. Again, I have, look at my miscellaneous topics playlist. I think there's, it's a nice lecture that I think I put in there. It's about 20 or 30 minutes, and it's really a pretty straightforward idea, and it's a very effective technique. I think everybody should be good at it. So, nevertheless, I'm going to say that this is an undesirable domain because, again, nobody really, all else being equal, if we can avoid it, trig substitutions are inconvenient. So, we do the pullback through polar coordinates. And I'm going to make the claim here that this undesirable domain is an image. It's a convenient image by the polar coordinates change of variables function. Now, let me try to persuade you that this is, in fact, an image. And we'll take this one little bit at a time. Let's think about this edge right here. This edge in the r theta plane has theta equals 0. We start at r equals 0 and go out to r equals 1. What does polar coordinates do to those points? Well, it makes that edge right there. Okie dokie. Now let's look at this edge here. That edge, you'll notice, r is constant 1, and theta goes from 0 up to pi over 2. Now let's follow that instruction over here, and notice that gives us this edge. Curve, part of the boundary of this thing. Okay. And then off we go, continuing. This edge is that. And then the last one, a little bit tricky, a little bit weird. This edge here, now theta goes from 0 to pi over 2 with r equal to 0 everywhere on that edge. That means all of those points go over here to where r equals 0, namely it goes to the origin. Right? So all of those edges go to what I've drawn over here, and therefore the image of this rectangle is this disk, namely our domain for our original integral. Is everybody happy? Okay. Yeah.
In an actual question, we not be given this square.
Correct. Yeah, I won't give you the pullback, but so if you want to use this, as I'm presenting it just for this moment, Yeah, we'd have to have to kind of think it through and kind of reverse engineer this process that we just argued to make this pullback domain. Good news, though, there's a better way, and I'm going to show you that in just a couple seconds. Yeah. Okay. All right, so we've got ourselves a pullback domain, and I'm going to say this original domain that I don't like basically goes away when I do the pullback, because after all, I have now my new domain, which is just a rectangle that gives me easy bounds for r and theta. When I slice up that blue domain on the left, right, it's a rectangle. So r and theta, just look at the picture, constant bounds, easy to identify. Now, that's how the domain plays out. That's all good. X squared plus y squared. Of course, now I've got to rewrite that in polar coordinates. Nothing to it. In this case, at least, x squared plus y squared is r squared. That was one of our pat formulas. Don't forget your stretching factor. Really easy to forget your stretching factor. I have a trick for that I'll mention in just a minute, but anyway, you do have to stick that in there. That's our way of recognizing how area in the XY plane is a stretched out version of area in the r theta plane. Again, really important to have that in there. It's such a big deal. And we've got ourselves a pullback. Everybody with me? All right. Okay, so now it's plug and chug. We've got this integral. Notice our integrand is r cubed. That's another thing. You got to be careful about this. The r here is not just there for cosmetic purposes. It is part of the integrand. A lot of people kind of forget that. Just kind of keep it there as for aesthetic reasons or something. But r cubed, you got to factor that into the original integrand. R cubed is now our integrand. And easy antiderivative, easy plugging in, and it's single variable calculus. Okay. All right. Cool. So here's the thing. Let me come back up to here actually for a quick second. Once we had our pullback domain, we slice it up. And so, for example, here's a bunch of slices. Those are what I'm going to call theta slices because they're perpendicular to the theta axis. And that's what they look like, of course, in the r theta plane. So I want to make a clever observation here. This is really convenient. These theta slices in the r theta plane, I can push them forward through this function and just see what do those look like. And keep in mind what they are. These are just lines representing a constant value of theta. What does it look like, I ask rhetorically, in the xy plane here if I say I want to look at lines representing constant values of theta? And, well, kind of like this. They're rays coming out of the origin. So I'm going to make the case that even though, yes, I am kind of technically doing a pullback and I have a new domain and I'm slicing in the r theta plane, everything that happens over here in the r theta plane, I can kind of see it happening in the xy plane. And again, it's really happening over here, but you can see everything that's happening over here. And then likewise, I suppose, for r slices, if for whatever reason you wanted to slice first perpendicular to the r-axis, turns out most of the time that's not a good idea. But if you did want to, these slices, r slices, just represent various constant values of r. And constant values of r are just like that in the xy plane. And so again, you can see what they look like without actually going over here into the r theta plane and seeing them explicitly. So this is a really, really powerful observation because of this. Since I can see what's happening in the r theta plane by way of what it looks like in the xy plane, I don't even have to draw the pullback. And this is very convenient. So now you'll notice this is the exact same example we were looking at previously. And here is our original domain that we don't like because of the curve and the square roots and the ugly and the trig substitutions, right? And I had pulled back and made a rectangle and then sliced and diced that rectangle. What I'm going to do here is, again, just pointing out that I don't need to do that, because when I slice, when I take theta slices perpendicular to the theta axis, well, here they are. These are what those theta slices look like. And I could just straight up see that the very first one here, where theta is equal to 0, yeah, okay, well, right, here it is. There's that theta slice where I can clearly see in the xy plane theta is equal to 0. And the last slice, that last slice there where theta is equal to pi over 2, yeah, I can see that here too. There it is, last slice, theta is pi over 2. So, I mean, conceptually, it's good to know that there is a pullback, and this is change of variables, and change of variables does the heavy lifting for us to find the stretching factor. But when we put this into action, when we actually implement and act, rubber meets the road, let's do it, right? You can see the whole process right here in the xy plane that you were given in the first place. So basically, the moral here is you don't really need to draw the pullback. Everything you need to see is right here. Okay, how are we doing? Is everybody with me? All right. Okie dokie. Oh, and of course, given as well that, if you have a given theta slice, and this is what that given theta slice looks like, I can see where R starts just as well in the xy plane, and I can see where R ends. Well, it ends on that curve where R equals 1. Again, right there in the xy plane. Yeah.
Could you go over again why you mean the R with the R?
So that's the stretching factor. So whenever you do change of variables, you have to insert your stretching factor, and that's what we computed over here in polar coordinates. Our stretching factor. Our stretching factor is, assuming we make the appropriate choices, R. Yeah. All right. So so let's do some more, and I'm going to do these next ones. There we go. I'm going to do these next ones without. Oh yeah, go ahead.
Yeah. For the stretching factor,
yeah.
If you had the domain for R from 0 to 2, will your stretching factor also be affected?
It's still the same formula R.
Okay.
So the formula does all the accommodating for us. That's no problem. As long as your R stays positive,
All right.
stretching factor is always R. Yeah. Okay, next example. Now again, we could draw a pullback and such, but again, you don't have to. Now I'm going to make the usual observation that with our domain being the unit disk, we really don't want to do this the regular way, slicing and dicing, because, oh my gosh, curves everywhere, square roots, nightmares ensue. But let's do this using the polar coordinates as a change of variables function. And what do our theta slices look like? Well, our theta slices start here, where theta is equal to 0. Let me make my color choices a little different here. So theta goes all the way around from where it had started at 0, and then it ends when you get back to where you had started. It ends once you've sort of swept out your entire region, right? And it ends, therefore, at, what happens to theta when you go all the way around? Theta goes up to 2 pi. So in my theta slicing, I'm going to have theta going from 0 to 2 pi. Neat fact, if your solid entirely encompasses the origin in its interior, theta is going to always be 0 to 2 pi. Nice convenient option. And then let's see here. Now for a given value of theta, let's fix a theta. Let's see here. Let's fix theta to be, I don't know, let's say that, whatever that is. Let's see, what's my starting value of r? Well, r starts at the origin, where r is 0. Yeah, there you go. And let's see here, r ends at that point. Be careful about this. That point is on this curve. That curve has what equation? Well, don't forget, this is the unit disk. That means that this is the unit circle, and that means that this is r equals 1. And so on that point, we have r equals 1. So for that value of theta, as we go from there to there, r goes from 0 to 1. Everybody happy? Yada, yada, yada. A bunch of, extra, it's all single variable calculus iterated integrals. Okay. So, some tips and tricks. I'm going to say basically always you want to put the dr on the inside and the d theta on the outside. There are counterexamples, but they're pretty manufactured, and I've never encountered one in the real world, right? In the wild, I've never seen an example where, oh yeah, it's really helpful if you go the other way. I basically don't worry about that, right? So I'm going to say always, asterisk, always put the dr on the inside. Now here's another little bit of advice with the understanding that we are going to do the dr on the inside and the d theta on the outside. Please don't write that down. Turns out I think it's a really bad idea. You should always, I encourage, write down r dr d theta all at the same time. Now why is that? Well, because that r, again, is your stretching factor. That stretching factor is what makes change of variables work. That r, one little factor, r, right, is the multivariable calculus part of this multivariable calculus technique, right? It's really important. But what happens, I'm just telling you historically, what happens when students look at an integral and they want to use polar coordinates like this, and they start thinking about, okay, well, what happens to theta and a theta slice and r and the equations of the blah blah, and they're thinking about these bounds, and they'll forget. So often, you'd be surprised. It's really easy to forget, right? To write down the stretching factor. Most important part, right? If you had to pick one single element of the solution that is the most important part of the solution, that's it. And it's so easy to forget. I've forgotten it myself before I adopted this rule. And my rule is don't write down your differentials dr d theta by themselves. Just write down r dr d theta together. Then you can't forget it. Does that make sense? I hope that makes sense to everybody. And it's just a psychological trick, and again, you don't have to, but you're leaving yourself vulnerable to missing. I mean, look, on a 20-point question, this r could easily be 4 or 5 points. All you got to do is write it down. Right? Get those points. Make sure to get those points as quick as possible. It nevertheless is always the case that some students will decide not to follow this advice and will forget and lose those points. And it's tragic, but it's got to be done. Does that make sense to everybody? Everybody with me? Okay. All right. Okay. And then, as usual, when you're trying to find your bounds, keep in mind that they come from understanding certain points that represent the starting and ending values of your slicing. Those points being on certain curves that have certain equations. Those equations are what you solve to get your bounds. It's just like every other slicing process we've ever come up with. Okay, so here's another example. Let's look at this question here. Our domain for this integral is this annulus. It's kind of a ring. For whatever reason, my head goes to this being a moat around a castle. Maybe I want to calculate how many alligators are in the moat. Whatever. how am I going to compute an integral on this region? Now, the very first temptation, a lot of clever students will come up with this idea, which is to say, well, let's take the interior region, right? We'll take the integral on that interior region, and we will subtract off the integral on, or subtract that from the integral on the outer region there, D2. So sort of purple minus yellow should give us blue, right? And geometrically, that's kind of satisfying. Let's see here. Let me put the blue on here. Right? Pretty satisfying to think that. Here's the problem. Big problem. As it turns out, notice that our integrand is undefined at the origin. And we have not defined what an integral means if the integrand is undefined somewhere in the origin. And this is not because we just haven't gotten around to it. There's a problem. It's a real problem. It's a serious problem of how to even make sense out of what an integral is. So notice that that problem point, the origin, that makes this yellow integral undefined. That makes this purple integral also undefined. So if you're interested in computing this blue integral, you cannot declare it to be the difference of two things that don't exist. Not possible. Okay, we in Math219. Okay. So look, you could do this in rectangular coordinates. Again, nobody wants to do this, but you could say it's that region and that region and this region and other color. Oh man, okay, this region. Right, so I could compute on those four regions, but again, obviously bad. Right? I don't want to compute integrals on four separate regions, especially when on each one of these, there's circles that make up part of my bounds. That means there's going to be square roots in my bounds. That means it's going to be ugly, right? This is going to be a nightmare approach. We don't want to do that. So polar coordinates to the rescue. There's nothing to it in polar coordinates. We start... Right, if you look at our theta slices, theta starts at 0. Theta then goes all the way around and ends at, when I get back to where I had started, by which time, of course, we're up to 2 pi. Right, so theta goes from 0 to 2 pi. And then for a given value of theta, we look at now at our r bounds. And r starts at that point, which is on that curve, which has that equation. Keep in mind, I'm interested in finding an r bound, so I need to solve for r in that equation. Okay, convenient, it's already solved for, that's nice. And so that is our lower bound for r. Right, and then likewise, we finish at that point, which is on that curve, which has that equation. Again, remind yourself, really easy to forget, I'm looking for an r bound. So in this equation, I solve for r, and that gives me my upper bound for r, which is 2. Easy slicing. I get constant bounds in polar coordinates. So we got rid of all those ugly, nasty square roots. Very convenient. Now, one last little detail we've got to keep track of. Don't forget our integrand. Let's see. Let me clean all of this up. Our integrand. That was kind of the big problem in the first place. Our integrand here is 1 over r, and there's a temptation to say, hey, don't we still have a problem here? But no, we don't. Look at the bounds on r, right? R goes from 1 to 2. 0 is not part of that range. So as r goes from 1 to 2, 1 over r, no issue, no problem. Perfectly well defined. Don't forget your stretching factor. And again, let's see here. There we go. I am a big believer that you should always write down your stretching factor as part of dr d theta. Right, so RD theta, think of this as a kind of a single thing. Write this down all at once. By the way, it is a single thing. This is dx dy. Right? DRD theta by itself doesn't really make sense in the xy plane. It's not a thing. It's not part of the integral we were asked about. Don't write down stuff that doesn't make sense. It's a good general rule, right? So RD theta, though, is dx dy. That does make sense. That is a thing, and it helps you remember to actually put that r in there. And then notice this turns into a super easy integral with that cancellation, and boom, we win. There are 2 pi alligators in our moat. If I can get this thing. There we go. Okay. All right, here. Another example. So this is another kind of weird one. I'm going to start with a disk. You all recognize this is a disk centered at 1 on the x-axis. And now what we're going to do is we're going to subtract off of that. We're going to cancel off of that anything that is in this red disk. Anything in here, anything in the red, we remove. Right? That's what this notation right here means. And so the picture is very straightforward. We're going to look at the yellow. We're going to take a big red bite out of it. And the result is, of course, what I have shaded in gray here. There's our domain. How would I do an integral on that region? Now, again, rectangularly, I suppose you could. Right? If you want to do this in rectangular coordinates, but you're going to be hitting corners and side-swiping edges, and best case scenario, that's 3 separate rectangular integrals with square roots in the inner bounds. That's no good in rectangular coordinates. Nobody wants to do that. So we look at polar, RD theta, written all at once. Really easy to forget that R if you don't do that, right? So I'm giving you the hard sell on don't forget your R. Write it down at the same time as you write down the drd theta. And let's think about what theta does. Well, here's a theta slice, and it starts here and it ends there, which I claim are these values, pi over 3 and negative pi over 3. Now, there's a couple of ways that you can find those. One thing you could do is you could observe that's where, for example, this curve intersects that curve. And you could solve for theta that way, and that's fine, no problem. Totally do that. I think there's a more clever way to make this realization, and that is to point out, and just noting just from the geometry, this little triangle right here that I'm going to pay some attention to. This edge is part of a unit circle, and so therefore has length 1. This edge is part of the same unit circle that therefore has length 1. Right? And this I've already used that color. This edge here is part of this unit circle, which therefore has length 1. Right? And so just at a quick glance, how convenient is that? At a quick glance, we can see that we have an equilateral triangle here, and that immediately makes this angle that I'm interested in, this the value of theta down there, conveniently pi over 3. Well, negative, of course, because we're polar coordinates and all that. Everybody happy? Okay, so there's our theta bounds. Now, of course, R, we've got to think about our R bounds. What does R do? Well, R on a given theta slice is going to start at this point, which is on that curve, which has that equation, which gives us, which gives us our starting value of R. Our R slicing ends at that point on this curve that has this equation. Now notice real quick, that equation wasn't given. Where did I get this equation from? Well, I had to first write down this circle in rectangular coordinates and then convert. Flashbacks to chapter 1 when we were first talking about polar coordinates. rectangular equations can be converted into polar equations by kind of plugging in and all that business. And this equation then, again, solve for r, gives us our upper bound for r. And it's all over with the shouting. Our integrand x, of course, in polar coordinates. Nothing to it. R cosine theta. Don't forget your stretching factor. So easy to forget. Please write that down all at once as part of your what used to be dx dy. And we have ourselves a relatively easy integral. I know it does have some trig inside of it, but trig integrals, we have techniques for trig integrals. They're not that bad. Totally doable. Okay, all right, that's a good stopping point for today. We will pick up here on Wednesday. See you later. Have a good one.